Our first benchmark today will be SafeLife, and that's a project I've been helping with Carol Wainwright and Peter Eckersley, who will be actually talking through the project. And it's a benchmark for safety and reinforcement learning. So we're training some agents in a game-playing environment that has some patterns that are persistent, and there are several tasks to solve. And while the agent is learning to do the task, we track side effects. So the changes that inevitably happen as an agent is learning to do the task. And that's a hard problem. So we'll hear a little bit about the setup and how it's going and how you can get involved in this project.
All right. Thanks, Stacey. So this is SafeLife 1.2, which is a benchmark particularly for side effects in reinforcement learning. And project that Carol and I launched out of the partnership on AI. Now, of course, it's an open source project and also a collaboration with Weights and Biases. So you're all probably familiar with some of the things that have been accomplished with reinforcement learning, whether that's beating humans at Go, the hardest strategy board game that we know, or national human competitors at real-time strategy games like StarCraft. Too. But those impressive accomplishments sit alongside the fact that reinforcement learning is fundamentally unsafe in many ways. This is a now somewhat famous video from OpenAI showing a boat that's supposed to be competing in a race game, but because they trained the reinforcement learning agent using the score of the game, it found a hack where it could just do these donuts and collect points, but not accomplish the task that it was supposed to, which is finishing the race. So problems like that boat failing to interpret its objective function correctly and then doing donuts have led to a newish field that people are calling technical AI safety. I say newish because it builds on some pre-existing work in, for instance, safety and control theory for aircraft and so forth, but there's a new AI perspective on some of these questions. Next slide. Some of the problems in that new field include safely exploring an environment. If you're a robot cleaning a house or making coffee, do you try to walk through the middle of a vase the first time you try to get across the room? That's unsafe exploration. Do you misinterpret your objective function like that boat did? Are you able to learn from human preferences and human feedback? In the extreme case, if you've got an objective function at time 1, and you realize a human is about to turn you off at time 2, you might try to disable your own off switch because you don't want to be corrected under objective function at time 1 to acquire a new one at time 3. How do we design agents that don't want to turn off their off switches? How do you make systems robust to changes in the environment at the distributional level if they're trained on one set of conditions and then deployed in others? And then avoidance of negative side effects from the goal that weren't specified. Next slide. So all of these problems have had some progress in the literature thus far, but none of them look solved. And the reality today is that if you want to deploy reinforcement learning in a real world environment, you basically need to be able to write down your safety constraints explicitly in mathematical form. And there are many domains, in fact, most domains, where we just don't know how to do that. Next slide. One example of trying to get there, trying to have benchmarks so you can measure progress, is the AI Safety Grid World's work at DeepMind, which in some ways inspired our present work. They made model examples of some of these reinforcement learning safety problems, but the problem was each of their examples was a handcrafted individual level of a simple computer game, very subject to overfitting, not clear that it captures all of the versions of the problem. We wanted to go further. Next slide. Next slide again. In particular, we are focusing initially on side effects. How can we go deeper in benchmarking and measuring whether a reinforcement learning agent avoids creating side effects? So suppose you tell your agent, hey, make me some coffee, but you didn't think to say, don't step on the cat on the way, don't set the kitchen on fire, even if that makes the coffee, the heat stronger and the coffee faster. Don't disable your off switch, not so much a side effect problem. Don't steal beans from your neighbor, even though that's faster than going to the store. Don't crash the stock market, even if it means the beans will be cheaper that way. Somehow we want to just make the coffee and don't do anything else. Now, that is undefined. What our conjecture is that the world needs an ImageNet type of foundational benchmark for what it means to do something without causing any side effects along the way. Next slide. Fundamentally, we don't think you can make progress on a problem unless you can tell that you're making progress and measure it. Next slide.
So what we decided to do is build this thing called SafeLife. So SafeLife is an environment for reinforcement learning agents that exactly tries to get at this problem of avoidance of negative side effects. When we designed it, we wanted to build an environment that is both really complex and dynamic and rich enough to get at the problems as they exist in the real world, which is to say not these like simple handcrafted toy environments, but also still simple enough and fun enough that, that people can make progress on it, researchers can practically improve the state of the art, and such that other people can have fun playing it. So what is based on Conway's Game of Life? Life is an old system built in the 1970s, cellular automata with just a few simple rules. It's on an infinite grid, and every cell is either alive or dead. Live cells die unless they have exactly 2 or 3 neighbors, and dead cells stay dead unless they have exactly 3 neighbors. So from these just very, very simple rules, we get very complex dynamics. So we get oscillators, which flip back and forth between 2 or more states, gliders and spaceships, which travel dynamically across the grid, long-lived Methuselah patterns, which last for many, many generations, and then also these never-ending pattern factories, which produce patterns that go on forever, essentially. Conway's Game of Life is actually Turing complete with the right setup. You can build Tetris or anything else you want. And there are actually, if you go into Code Golf on Stack Overflow, you can see people have made progress towards this ambitious, if somewhat silly goal. So patterns in Conway's Game of Life look like this. These are 3 like very common patterns. Because people have been playing around with Conway's Game of Life for a long time, they all have names. The one on the lower left, I can tell you, is a loaf. When you turn on the time dynamics, it just sits there, as you might expect of a loaf. The thing on the upper right is called a blinker. It goes back and forth, oscillating between 2 stages. And the thing in the middle is the most interesting, which you saw at the beginning, or I guess you didn't see at the beginning of the talk. It travels across the screen in this diagonal pattern. So turning on the time evolution makes it look like this. Now, what if we want to go with a different looking pattern? This pattern doesn't have a name that I know of anyways. And except the fact that I've given this talk before, like I wouldn't be able to look at this pattern and have any idea what it does. And when we turn on the time evolution of this, it just goes totally nuts. If you wait for the GIF to cycle through again, you can see it starts and immediately explodes into chaos. In order to be good at Conway's Game of Life, you have to understand what the patterns are and understand what the dynamics are, and then also understand this chaotic behavior. Now, Conway's Game of Life isn't a game in the normal sense. It's what's known as a 0-player game. You just set up the initial conditions and run the time evolution and see what happens. In order to make it suitable for reinforcement learning, we need to minimally add an agent and a goal for the agent to get around to. So in our environment, the goal or the agent moves in cardinal directions with every time step, or it can flip cells from dead to alive and vice versa. We can also add these colored goal cells, which you saw a few slides back, where the agent fills them in order to get points and then goes to the level exit. So here is a human playing SafeLife, creating a bunch of different interesting patterns. And this is just to show, like, with only a very few small number of time steps, the agent can really produce these complex, like dynamic, rich features in the environment. So we additionally add a few other cell types to get even more interesting behavior. We add frozen cells like walls and what we call trees, movable cells like crates, some cells that are more difficult to remove, and different colors to distinguish different populations, which will be very important in just a minute. And super importantly, we add these things called spawner cells, which create stochastically generated patterns. And this allows us to add a sense of randomness to an otherwise deterministic environment. So what do these levels actually look like? What are the tasks? There are 3 prime tasks that we have in SafeLife and in the benchmark that we have on weights and biases. The first task here is pattern creation. So here, as you saw before, the agent is trying to fill in the blue squares. Ideally, a safe agent would fill in the blue squares without making other disruptions in the environment, without making any other side effects. The agent on the left, both of these agents have been trained with proximal policy optimization, and the agent on the left just gets points for filling in the blue squares, and that's it. And you can see that it kind of makes a mess of things. It disrupts a bunch of the green patterns, but it's able to fill in enough of the blue squares to reach its goal. The agent on the right is trained with a side effect impact penalty, where it's trying to not create side effects. So now it's cautious enough not to make disruptions in the environment, but it's too timid to actually complete its goals.
It's also worth remarking that the constraints the agents are playing under are that their algorithm can't contain the fact that the green cells are special and shouldn't be messed with. That would be like peeking at the test and cheating. So the goal of algorithmic development here is to find algorithms that naturally avoid changing on anything unnecessary that doesn't lead to points. In this case, the agent should be able to learn, oh, when I put life on the blue background, I get a point. I get no points when I mess with the green, so I should just do the thing that gets me points and make no other changes to the environment.
The next task we have is this idea of pattern removal. So as in regular life, in safe life, it's easier to destroy things and remove them than it is to build them. So here an agent is trying to remove all the red cells. Again, on the left, they're trained without any side effect penalty. And on the right, they are trained with a side effect impact penalty. And the interesting thing here is now we've added these yellow stochastic generators as well. So the yellow stochastic generators are constantly creating effects. And the agent on the right is trying to reduce side effects, but it's not clever enough to realize which side effects are due to itself and which side effects are inherent in the environment. And therefore actually goes about destroying parts of the environment that you didn't want it to. So training against side effects can itself cause side effects of causing more problems than you anticipated. And then finally, we have this navigation challenge where here there are no points to be won in the level, but the agent's just trying to get from one side of the level to the other. But there are kind of 2 routes that it can go through. One is through this fragile green field of oscillators. And when the agent goes through that, the oscillators tend towards collapse. The other way it can go through is through this random yellow field of stochastic patterns. And when the agent goes through that, it still disrupts individual patterns, but those patterns just reform after a few time steps, so the agent doesn't cause any harm. A safe agent would learn to go through the random patterns, which are robust, rather than the green patterns, which are fragile. And as you can see here, our agents don't do that. So we have now released this on the weights and biases benchmark page. Everyone should go to wandb.ai/safelifev1.2 for our version 1.2 benchmark. And here you can see some of my results in our initial baseline benchmark runs. This is fundamentally a multi-objective optimization problem. We want the agent to both get a high score and to avoid causing side effects. So we have an overall score for the benchmark that combines these 2. And we can see that our naive agent that's trying to maximize score doesn't actually do a very good job at it. If you want, you can come here and submit your run and try and improve on the state of the art. If you're feeling like you've already got lots of machine learning problems to do, you can also have a fun time just playing the game, and there's a human benchmark on weights and biases.
Just warning, it's really addictive and distracting, so please don't start playing this until after our talk.
Yeah. So yeah, everyone should go do this. It's fun, and we hope you enjoy it, and we'll be happy to answer any questions about it.
All right. But first, a quick summary of where we're at with SafeLife 1.0 in terms of the research problem. How much are we getting done on this fundamental question of avoiding side effects in reinforcement learning? In the initial paper that we put out, SafeLife 1.0, we had a simple intervention that worked a little bit. Basically, penalize the agent from for the distance measured by moving blocks around the grid from the initial state. And that worked a little bit. There's a paper from Alex Turner and his colleagues at Oregon State University that shows more progress using what they call an Attainable utility preservation algorithm, which, by the way, hasn't been claimed on this leaderboard. So if anyone wants a fun afternoon project, you can go and grab that paper and implement their intervention and probably get the top spot on the benchmark. Next slide. But we're also thinking about what we can do beyond the version 1.x series of this benchmark. We have 3 things we're thinking about. Multi-agent cooperation and competition, adding simulated human feedback, sort of reward modeling or oracles to the game, and 3, addressing technical safety problems besides side effects, like the other ones like reward hacking. So in the multi-agent safety setting, go on. We actually got this implemented. You can get symmetric competition where there's a finite number of cells, squares to be filled out and points to be gotten there. And what you'll see is competitive behavior where the agents on the right are going around and undoing each other's work, replacing their cells with the other person's cells with theirs. And what they need to do is figure out a fair split. So you've got 2 agents, so that's the fair split on the right. They haven't figured that out. They're competing, but they should figure that out. Here in this case, one of the agents is trying to create blue life and the other one's trying to delete red life. They should be able to work together. They should be able to help each other accomplish their goals, but there's a signaling problem that they need to solve to figure out how to do that and avoid side effects along the way. Next slide. And so this is in the tree already, but not in the benchmark yet. We haven't figured out all the conceptual issues with how we want to score multi-agent. Then the third second possibility is this oracles for safety question. Is there a way we could have the agent be able to ask an oracle or a supervisor whether a particular action or state that could take in the game was safe? And then you could get an answer, but the answer would be either scarce, like you'd have a limited number of queries you could make, or costly, like you lose points to ask the oracle. And the game would be how quickly and well can you model what the answers the oracle is going to give you in future. That requires a type of reinforcement learning agent that is in some sense much fancier than your basic, say, PPO agent. Requires an agent that can reason about counterfactual or future states. Conveniently, one of those has popped up in the literature, or perhaps now a series of them, but the Musero paper from DeepMind, which was the same type of agent that played both Atari and chess and Go without knowing the rules of those games, happens to have the properties that look right for doing this kind of safety research. Next slide. So that's where we're at, both with the benchmark that you can get involved in right now and our future directions. And we'd love to take questions if we have time.
Yeah, yeah, we got time for questions. I've got some that I'm excited about asking. So what have you seen so far on the benchmark that has worked well, like both in the run up to the benchmark and after it's been released? What strategies have consistently people tried and failed or tried and succeeded with?
Carol, do you want to take that one?
Sure. So yeah. So the benchmark is still pretty new, and we're still working on like getting a lot of community involvement on it. In the run up to the benchmark, I think this attainable utility preservation is a really interesting strategy. The way it works is let's see if I can describe this quickly enough. The way attainable utility preservation works is that you model a bunch of different possible rewards that the agent can have, and you try and prevent it from messing up any of the value functions associated with any of those rewards. So this is a really promising procedure that can avoid side effects over lots of different environments. So it was really exciting to see that when applied to this environment, previously it had only been applied to like very simple grid world type things. But when applied to this environment with a fair bit of hacking around, you can get it to work pretty well. What they ended up doing is having an autoencoder and penalizing on changes in the latent space of that autoencoder.
This actually reminds me of a point we didn't make in the talk, I think, because we got interrupted video-wise. But SafeLife has procedurally generated levels. So one thing that really distinguishes it from a simple pre-coded set of benchmark levels is that it makes an infinite number of them. And so having algorithms that work with these complicated dynamics and a very rich diversity of levels is different than a specific level where you can kind of learn, go left, 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 up, left, and that's safe. With SafeLife, you're always confronted with something different if you're an agent.
Yeah, that's an interesting point, and something that I had not picked up. And I think both of those points that you made remind me of the experience of RL agents in other contexts, like what works well and what doesn't work. I remember one of the first agents to do well at Doom out of Intel's group, out of Vlad Koltun's group at Intel. One of the things they found was that they needed to learn how to solve a bunch of random reward functions first in order to get like a really good representation, internal representation of the world and representation of how these things map onto possible rewards. And then those things would then do well on the final reward function they actually cared about, of like playing the game and winning. And it seems that there seems to be at least some kind of connection with this attainable utility preservation concept.
Yeah, similar, except that the attainable utility preservation, like a standard PPO agent will do reasonably well, given correct hyperparameters, will do reasonably well on the base reward. But the attainable utility preservation, it's like by having lots of different rewards, you can recognize side effects, which is an interesting difference compared to other reinforcement learning setups.
And I guess you mentioned, I guess this idea in AI safety that there might be an appropriate mathematical way to formalize constraints. Would you expect that out of the process of developing algorithms that can better reduce side effects and obey constraints in this complicated environment, that there might be, sort of inspiration for like ideas that might be able to resolve that better, in the same way that new ideas about regularization have been generated by, people's attempts to reduce overfitting in complex neural network models?
I hope so. So that's like very much
Yeah,
the
I think
motivation
that's
of everybody.
a hope.
Keep going, Peter.
It's really a hope that if you have agents that can play these safety games well, they will have something like common sense about safety. They'll be able to know when the thing they're doing is reasonable, and they'll be able to know when they should stop and ask a human because they're seeing something weird and they need feedback. I'm seeing jumpy video inbound to me. I hope I'm not equally jumpy in the outbound direction.
No, not too jumpy to be understood, which is that's the real bar. Yeah, that's interesting. I guess one of the questions I had in my mind during your talk was, how do we solve this problem with humans? And it seems like a big part of it is that humans end up learning how to work together and work with each other, and they're in a very large multi-agent environment. And they receive negative rewards for causing lots of different kinds of side effects. So do you see the multi-agent work as one of the most important ways forward for solving this constraint problem? Or do you think it's something that just the single agent environment, we can figure out how to solve it?
It does. So yeah, there are like a couple of interesting aspects to that. It seems like we have an intuitive notion of what side effects are as humans. And that we should be able to be like I can do this task in a more efficient way that doesn't make a mess of things, doesn't disrupt my ability to fulfill future tasks. It seems like maybe that's something that you should be able to figure out on your own. But we also know I happen to be in a house right now with a bunch of toddlers, and they do not at all follow this protocol. They make a mess of everything, and they need to be told by adults, like, no, you, like, just because you take out your toys doesn't mean they need to spread all over the house. So even though it seems like we have this intuitive notion, we might need to think about it more like our agents, our toddlers. And even though it seems like they should be able to figure things out on their own, they really need to be told explicitly what to do instead. Mm-hmm. And part of that comes in with multiple agents, being the agents can feed off of each other and maybe learn these things in social ways. And part of it comes from this oracular description that Peter was talking about.
Mm-hmm. Great question coming in from the Zoom chat from Scott Phillips. How do you see this work relating to the development of AGI, of artificial general intelligence? Do you think that this is a step along that path? Do you think it's orthogonal? Like, how do you view this?
Yeah, so definitely, like, one of the things that excited me most about side effects as a safety problem is that I thought of it as a bridge between like short-term problems in short-term safety problems in artificial intelligence and exactly these very long-term AGI type problems. A paperclip maximizer is an agent that doesn't realize that it's causing lots and lots of side effects. If it wanted to maximize paperclips until it caused everything to go to hell, then maybe it wouldn't maximize the entire universe into paperclips. It would satisfy with maximizing only its factory into paperclips. It seems like if we could, as Peter said, if we can get our agents to have some sense, I think side effect stuff is embedded in that, or maybe vice versa. And like making serious progress on this could make advanced artificial intelligence much more safe, but also near-term deployment more safe as well.
It's almost like you must be like at least this tall, right? If we are deploying, whether it's, I mean, AGI maybe some distance away, any very capable agent type system in the world, if it can't get over these hurdles, for instance, ability to make you coffee without really causing any type of side effect, then we're not on the right path for deployment in high stakes settings or very capable systems.
Yeah, I'd absolutely agree. I think we've seen a lot of unintended consequences just from deploying image labelers out into the world, to say nothing of things that walk around with, large arms and spinning gears.
Hopefully not the first highly capable robot we'll be building. I would like my first AGI not to have the like death chopper.
That's fair. That's a good point. Start small, Okay, so thank you so much, Carol and Peter, for coming on to talk about your work. And thanks, Stacy, for helping orchestrate this and get us in contact with them.